you actually already have experience with related rates. And, if I... Let's try that again. Okay. If I told you that y equals 3x squared, you would tell me that y prime equals... Don't you wish they were all that easy? In other words, the way that the rates of x and y are related is that the rate of change of y is equal to 6 times whatever the x value is for that function. Okay? So that's how the rate of change of y with respect to x is related to x. So that's a related rate. We're relating the rate of the function y to the variable x. Does that make sense that this is a relationship between the rate and the function and the variable? All right, so we're going to start looking at functions that are related to each other, but not necessarily directly related to each other. They might be related to each other through another variable. And I was actually thinking this is a lot like the predator-prey project you did last year, where the owl, I forget it was fox and rabbits, okay. The fox and rabbit populations were related to each other, but what they depended upon was... All right, hawks and owls, hawks and...
They were organisms.
All right, but what did their populations depend on?
Populations of as one gets
Yeah, I know they related to each other, but before they related to each other, they relate to something else. As a matter of fact, their populations were functions of what? Time. That was good. All right, so what we saw was the fox, or whatever, the hawk and owl population were functions of time, and that as you looked at them as functions of time, they actually related to each other, right? So that was sort of like a related rate. Like the functions were related. Thank you, to one another, but not directly. They were directly functions of time, and they were related by time to each other. So that's what we're going to look at today. And it's actually, if you think about the fact that what we're looking at today are two functions that are related to one another, as opposed to functions in a variable. What the problem we just did here was how a function is related to a variable. We're going to look at how functions are related to one another. And if you remember that when functions are related to one another, you need to do things like implicit differentiation and use the chain rule, then you'll actually catch on to the strategy we need to use. Okay? So I'm going to, I thought. All right. I'll start by looking at 20 from the classwork. So 20 starts us off with a ruptured tank leaks oil that spreads out in a circular pattern. So can you imagine this as the oil leaks out around the tanker? It spreads out in a circular pattern. Yeah. All right. And the radius increases at a constant rate of 2 feet per second. Can we think about that for a second? No, I don't know. How fast is the area of the spill increasing when the radius of the spill is 60 feet? So if we draw ourselves a picture and we have some radius here, the radius gets bigger. Every second, how big does the radius grow by? 2 feet. The question becomes, okay, when the radius grows 2 feet, how fast is the area increasing? Can you see that the area and the radius are two functions? Yeah. And can you actually see that they're going to have different rates of change? Like, you wouldn't say that the area is going to increase at a rate of 2 feet per second. Not only doesn't it not make sense, but it might not be true, right? 2 feet, how can the area increase by 2 feet? What do you want to say?
No.
You sure?
Yeah, I'm more.
So, the important thing here is I don't know that one's the derivative of the other, but
Well, like,
the rates are related. As a matter of fact, if the radius gets bigger, what's going to be true about the area?
the area's gonna get like even larger.
It's going to get bigger, right? If the radius got smaller, if it shrunk, what would happen to the area? It gets smaller. So these rates are related. They definitely are, but the important thing here is that area is a function of time and the radius is a function of time. And we need a way to relate these two rates. So, first things first, I just need some formula that uses the area and radius functions and brings them together. Does anyone have an idea? Say again. The area is equal to pi r squared. So that is a relationship that relates the area function to the radius function. Notice I didn't say radius variable. I said the radius function. So if I want to talk about rates, what do we usually do if we want to talk about rates? Derivatives. You take the derivative. Okay. I'm going to write this sort of specifically. I'm going to write it using Leibniz notation instead of Newton's notation. Newton might say like A prime, right? I'm actually going to do dA dt. Good.
It's essentially about to happen.
Maybe.
I know. I'm sorry. I'm thinking. We're doing the derivative of a, right?
Yes.
Isn't that just 2 pi r, which is also the circumference? This is ridiculous. How have I not realized this?
That's Asa notice is a very interesting side note. That the derivative of the area is 2 pi r, which actually is the circumference. And if you hold on to your seat, the next problem we do, you're going to get even more excited, I think. Did we talk about that in geometry like 3 or 4 years ago?
No? We
Okay.
talked about how they're like directly related.
All right. So I could find dA dr. I could find the derivative of area with respect to the radius. But the important thing here is that the radius is a function, and it's a function of time. So the derivative of area with respect to time is, how do I take the derivative of pi r squared? Okay, 2 pi r. But since r is a function, times r prime. Is that like implicit differentiation?
Yes.
Right? It's like the chain rule. It is. Now, I'm not going to write r prime. You can write it. I'm going to be more specific. I'm going to write dr dt. Okay. Can I show you something that might confuse you? Some people might just say, look, dA dr is equal to 2 pi r. Do you agree that the derivative of a with respect to r is just 2 pi r? Watch what I can do. I can take both sides and multiply by dr dt. Just like algebra, multiply both sides by the same thing. What happens to the drs? And on this side I get dA over dt equals 2 pi r dr dt. Right? Just what I wanted to end up with over here. Okay? But the really important thing was that Betsy reminded us and Zach said that the area and the radius are both functions of time. So I think I can get rid of, I don't need this. That was a nice aside, but I don't need it. Okay, so I now have an equation that doesn't just relate the functions, this relates the rates. It tells me, look, the area increases, the rate of change of the area is 2 pi r times the rate of change of the radius. This is the equation that relates the rates. And once you have an equation that relates the rates, you can go back and start plugging in. Well, I want to find out how fast the area is moving when the radius is 60. Oh, but I need to know what dr dt is. I need to know how fast the radius is increasing. They told me that. Actually, I'm going to use some units. I'm going to put 60 feet in here, and then 2 feet per second in here. And I think I'm going to get 240 pi. And what units am I going to get? Try again. Feet times feet, right? So feet squared, does that make sense, per second?
Yeah.
Why should it be feet squared per second?
Because you're looking at an actual, it's an area.
It's an area. And that's actually how fast the area is increasing. When the radius is 60 feet, the area is increasing 240 pi square feet per second. Just out of curiosity, what if the radius was bigger in this problem? What if the radius was 100 feet?
It would be increasing or higher. But the area would be bigger.
The area would not just be bigger, but it'd be increasing faster. So that's sort of interesting. If you think about like a circle, as the radius gets bigger, the area gets much bigger, right? Doesn't that make sense? It's pi r squared, right? You're squaring, right? Yeah, not just a linear thing. You're right. It's an area where it's getting bigger all around. And I think that's right. If you think about pizza, don't they usually have like the 12-inch, the 14-inch, and the 16-inch, the small, medium, and the large, something like that? And this is the radius. No, this is the radius? Yeah, it's the is it diameter? No, that'd be a really small pizza. It's a radius. 16-inch radius? That'd be like a big, 32 inches? That's like 3 feet. That's a big pizza. Wow, okay. So, is the diameter? 16 inches. No, that'd be small. All right, fine. All right.
It's like this big.
All right, so you want me to call it 6? So you want me to call it 6, 7, and 8? R. All right. So look, these are the radii. If this is like, I don't know, $10, $12, and $14. If the price is going up linearly, the area is actually going up quadratically. As the radius increases 2 inches, the area is increasing much more than 2 inches. So you're better off buying the large pizza. You get more pizza for your buck. Don't tell me you don't learn anything useful in calculus. How was that? We're going to do a few more, but do you want to ask some questions on that? You should. And you should tell like your mom or dad like that I told you to. Yeah, I mean, those pizza people could be onto this. I'm guessing they are. Okay.
Pizza Hut made that rectangular pizza, that enormous one. So that's the one.
All right. Air is blown into a spherical balloon.
3/4 pi.
No, three halves.
I am never going to remember.
3/4.
Where are they? Front of the book. And all right. So that's a good question. That's a good question to ask. Not yet, but it's a good question to ask, and we should have this conversation closer to the test. And your question should be, okay, Mr. B, we've been doing these problems for like 2 or 3 weeks. These are the things that I know so well because I've just been doing them, and these are the things that I'd really like it if you'd put on the test. And we can have that conversation. So like, yeah, maybe the volume of a sphere, maybe everyone doesn't know that it's...
3/4 pi r cubed.
You tell them, Gabby. 4/3 pi r cubed. Yeah, that's awesome. They're in the back of your planner, someone said, in the other class. So they're there for you to find. So don't tell me you can't find them, but you can tell me how much do I have to memorize. And we're not ready to talk about that yet, but we can be. So here's the volume, 4/3 pi r cubed. This is a relationship that relates two functions, volume and radius. It doesn't relate any rates. So for A, it says, at what rate is the radius increasing when the radius is 15 centimeters? So in other words, I have to find out an equation that relates the rates. What relates rates? Time. They're both functions of time, and when we want to relate rates, we're going to take the derivative. Awesome, well done. Okay, so over here, I'm going to get dv, and again, I'm being very deliberate using Leibniz notation, dt. And over here,
dr over dt. Power roll is 4 pi r cubed squared.
4 pi r squared, and don't forget
dr over dt.
the chain, which is dr dt. Asa?
Yeah.
I don't know if you're excited, but 4/3 pi r cubed and 4 pi r squared. This is the volume of a sphere. 4 pi r squared is the surface area of a sphere. Okay? You now have an equation that relates the rates. Once the rates are related, now we can start plugging things in. Okay? So, do I know what the rate of change of the volume is? Try again.
80.
It's 80. It tells us, right? Air is blown in at a rate of 80 cubic centimeters per second.
Wait, what?
You know what the notation of that?
Is that with the radius?
Not yet, right? This. All right. I also know that the radius is 15, and I'm trying to find out how fast the radius is increasing. All right.
I thought the 80 was the rate. How fast it is increasing?
Nope. When you blow air into a balloon,
Volume is increasing.
right? Now, I would agree that the radius is also increasing. This is true. The rates are related. But I can actually look at the units. The units are very helpful. So cubic centimeters is telling me the volume is increasing.
So you just solve for.
Okay, so let's see. dr dt, all right, 20 over 225 pi, 4 over 2040, 4 over 45 pi, I think.
Wait,
I'm doing that in my head.
wait. Where did you get that whole bottom part?
Well, I know I have to divide by this. 15 squared is 225 pi, and 80 divided by 4 is 20. So I did 80 divided by 4, and then I put it all over 15 squared pi. What's that about? 0.08? Really? No, it's not, is it?
Yeah, it's just a little under a 10.
No, but it's 4 over 45 pi.
0.279.
0.028.
No, 0.2792.
Is that right?
No, 0.028.
Point.
No,
It should be
you're
less.
You're not doing the pi.
It should
You're
be
not
less.
doing the pi.
It should be 4 over
How
45 point times 3, which
Okay.
will make the denominator
That's
bigger,
his
and when you make the
Oh.
denominator bigger, you
It's
can do the same.
0.028.
lower.
Okay.
Yeah.
All right. 0.028.
Yeah.
What are the units?
Inches squared.
Oh, we're using
Just
centimeters.
inches.
They're just
It's the
inches.
radius.
It's
We're
not
just doing
it's not an area.
Centimeters
Oh.
Per second.
per second. It's a rate. It's a rate, right? All right, let's try B. B says, at what rate is the surface area increasing? All right, well, the surface area of a sphere, Asa,
4 pi r squared.
4 pi r squared. Now, that's a relationship between two functions. I want to find the relationship between the two rates. The derivative of 4 pi r squared, 8 pi r. All right, so 8 pi, what's r equal to? 15. But I don't know what dr dt is.
Yes, you do.
Yes, I do, Gabby. Where is it?
0.028.
0.028. I just found out what that was. And you can actually, if you wanted to, you could leave it as 4 over 45 pi. And let's see, the pi's will go, and I'll get like 80, 120, 480 over 45. I don't know what that's equal to. Is that right?
It's like 10.6 feet.
10 and 2/3. And what are the units on this?
Square.
Centimeters.
Centimeters squared.
Yeah.
Surface area.
Per second. Surface area changing with respect to time. Centimeters squared per second. I'm tempted to do the last one because we have like 30 seconds left, but do you want to ask a question? Does it seem like implicit differentiation and the chain rule and all that?
Wait, when you're referring to the radius, it would only be like centimeters, but if you're doing like surface area or volume, it's centimeters squared.
Surface area would be centimeters squared. Volume would be cubed, right? Because we're measuring a cubic amount.
With the three-dimensional object.
C talks about the circumference. Well, I think the circumference is 2 pi r. So the rate of change of the circumference, 2 pi times, what's the derivative of r? R prime, which is
0.028.
dr dt, which is
0.028.
0.028. So we could actually just do 2 pi times 4 over 45 pi, and I think the pi's go, and you get 8 over.
You get like
45.
2 2/3 centimeters.
Wait, 2 and 2/3?
You get 2 2/3.
How could we have got? Yeah, sorry. Oh no, all right, that works. Okay.
2 times 15 times 4.
0.2 or something?
I don't see any 15.
8 over 45.
No, what about the...
7.
What happened to r?
I don't know.
What's the derivative of r?
Oh.
Actually, this is interesting. The circumference has nothing to do with the actual value of r. The surface area and the volume both actually depended on what the value of r was.
Uh-huh.
The circumference doesn't. And centimeters per second. And I think that makes sense, because the circumference and the radius increase directly proportionally, because they're both in linear units of measure. So look, tonight's homework's going to be painful. It'll make you cry. The first one's really, really easy. Don't overthink the first one. But the next 3 or 4 are going to be hard. But it will be better. It will get better.
I'll hold you to it, Mr. Bishop.
Have I been wrong yet?